y'all doing? My name is Ahmad Badawi, and I'll be presenting a 6-minute talk about the laws of thermodynamics, the first and the second laws. As for the first law of thermodynamics, it's basically saying energy conservation law. So basically, we learn either in physics or chemistry that energy cannot be created nor destroyed, but it can change from a different form to another. And here we have the first law equation, where internal energy equals the heat minus work, noting that the sign of the heat and the work can change based on if the heat is going on in or out, or work going in or out. If heat is absorbed, that's a positive value of heat. If work is done by the system, that's also a positive, while released and on the system is negative. Here we have a cylinder piston cylinder on the graph shown. Assuming in the first piston cylinder that the piston is pent and cannot move, if we heat the gases inside, the temperature and pressure is going to go up, but since the piston is pinned, it's not going to move, and since work is force times distance, work is going to equal to 0 since there is no change in distance. But in the second one, if we assume that piston is free to move, and we heat the gases inside, the pressure is going to go up, the pressure is going to up, so the piston is going to move up, and the change in distance is going to be used to calculate for work. As we know that pressure equals force over area, then we can find the force is pressure times area, and we can plug it in the work equation, where it's going to be force times area times the change in distance, and area times the change in distance as change in volume, and that's how we can find work. We have 4 processes that are commonly used in the first law of thermodynamics. The first one is the constant volume. That's basically the one I just explained, where the piston is pinned, so it's not going to move, so work is going to be equal 0. The second one is isothermal. Isothermal is basically temperature is going to be kind of constant, and that can be achieved by heating up the gases at a very slow rate, where the change is going to be 0 throughout the whole process. But since we're heating it, the distance is going to be there, change in distance is going to be there, so the heat and work is going to be calculated. That's why the internal energy is the only one that's going to go to 0. The third one is adiabatic. We also know heat is equal to 0. And isobaric, that means the change in pressure is 0, but that doesn't mean the pressure is 0, so we can still calculate for work using the regular equation, pressure times the change in volume. Here we have the second law of thermodynamics. The second law of thermodynamics basically explains the direction of heat, where it goes from hot to cold. As seen in the equation, that we have a high temperature going down to the low temperature, and the heat can never go from low temperature to high temperature. Also, heat cannot just go straight to work. There is always heat loss. This is where Clays's equation comes in, where it's saying the change in heat to the ratio of heat to the temperature is always less than 0. That means the inlet minus the outlet is always less than 0, because there is always heat loss. And the second law of thermodynamics is known as well as the entropy law, and the entropy is the inherent disorder of the system. That means the universe is usually have a tendency to go to disorder rather than go into order. If you break a glass of water, that's more likely than the shattered glass going back to the original form. That's what means there is a disorder. And it can be calculated, the equation, the change in entropy equals the ratio of heat to the temperature. And the entropy of the universe is always positive. And I just explained the glass thing, where it's always like that. And it can be calculated by adding the change in system plus the change in surrounding. That doesn't mean there is never a negative value of change in entropy. We can imagine like having water, for example. Liquid is basically more disordered than solid. So if we go and freeze water, that's basically a negative value of change of entropy. But for example, we put in the the freezer. The heat outside of the freezer is going to go up for the cubes to freeze, and that's going to create more disorder to the surrounding, more than it's going to be doing more order. So that's why the change in entropy in the universe is always positive. And the reason I chose to discuss the first and second order of fluid dynamics is because they're most common to use. And the zeroth law. The zeroth law basically tells us that if we have two particles that they're both in equilibrium with a third object, that means that all three are equilibrium with each other. And the third law of thermodynamics basically says if we have a pure crystal and it's approaching the absolute 0 degrees, entropy is going to be constant. And then that's it. Any questions?